Well, students, in the last two lectures, we have introduced matrix norms and subordinate norm to a given vector norm. We are now in a position to introduce the concept of condition numbers of a given invertible matrix. This is a basic tool in the error analysis of iterative methods for linear systems. Therefore, it is very important for us. Well, instead of directly introducing the formula for condition number of an invertible matrix, let us first prove a theorem which clearly tells us why this particular formula is important in our study. The idea is very much similar to what we did in the context of functions in the last chapter, where we introduced the condition number of a function. You just go back and recall how we have motivated the definition of condition number of a function. The idea is exactly similar in the case of matrix also. Let us state the theorem first. Assume that we have an n cross n invertible matrix and we are interested in solving the linear system Ax equal to b for a given b. But somehow we are not having this b, but we only have an approximation of b, let us say. Therefore, we will be actually solving the linear system Ax equal to b tilde, which is the approximation of b. That is, its components are not exactly the same, but it's very close to the components of b. That is what it means. Let the solution of the system with exact b be denoted by x, and the solution of the system with b tilde as right hand side is denoted by x tilde. Now the question is, what is the relative error in x tilde when compared to x is the question. But this may be little surprising for us how to obtain the relative error in a vector, because if you recall, the relative error is x minus x tilde divided by x, right? So it's not very clear how to define the relative error when x is a vector. But that is not a problem. We can always fix a vector norm and take the vector norm in the numerator as well as in denominator, and then call this as the relative error in x tilde when compared to x. And this is what we will be doing in our analysis. With that, the relative error in x tilde when compared to x can be estimated by this quantity. That is, the relative error in x tilde is less than or equal to norm A into norm A inverse times the relative error in b tilde when compared to b. Here you should note that this represents the matrix norm, whereas this represents the vector norm, where this matrix norm is the subordinate matrix norm with respect to this given vector norm. It means in this theorem, we are given a vector norm, and then we generated the corresponding subordinate matrix norm from that vector norm. And then we are using these two norms in the estimate. We should keep this in mind. It's very important. So with this, the relative error in x tilde can be estimated as some number which is given by this times the relative error in b tilde. By looking at this and connecting it to the definition of condition number of a function, you can immediately guess what will be the definition of condition number of a matrix. But let us postpone the definition of condition number of an invertible matrix little later. Let us first prove this theorem. Well, we are given two systems. One is Ax equal to b, right? Another is Ax tilde equal to b tilde, right? Since A is a matrix, you can always write it as A into x minus x tilde, right? And that is equal to b minus b tilde. And since A is invertible, therefore we can write x minus x tilde equal to A inverse into B minus B tilde. Now what you do is take norm on both sides. Remember, since I'm taking norm on a vector, this notation is actually vector norm, and similarly this is also a vector norm. We never distinguish notationally between vector norm and matrix norm. As I told in the last class, one has to understand them in the way they are used. Okay, just because the notations are same, don't think that this quantity and this quantity, they both share the same formula. No, they have entirely different formulas, but notationally they are represented in the same way just for the notational convenience, with the hope that there is no confusion in this. Okay, this is just a remark. Let us continue with our proof of the theorem. Once you see this, you can recall our one of the properties of the subordinate matrix norm discussed in the last lecture, and that is, if you have a x equal to b, which is the vector norm, that is less than or equal to the subordinate matrix norm on A times the vector norm on X, right? Now, you replace A by A inverse and X by B minus B tilde, and see that norm of X minus X tilde, which is actually this, is less than or equal to norm A inverse, right, into B minus B tilde, correct? That is what we will be writing here. Now, if you go back and see, what we wanted to prove is slightly more than what we got. What we want to prove is norm X minus X tilde divided by norm X is less than or equal to this quantity. But what we got is norm X minus X tilde is less than or equal to norm A inverse into norm B minus B tilde, right? This is what we got. So what lack now is to divide this quantity left hand side by norm X, and that should somehow bring us one norm A here and norm B in the denominator, right? That is what we want. So naturally what we will do is we will divide both sides by norm X. Of course, in all this, you have to assume that X and B are non-zero vectors. Although we are not writing it explicitly in the statement of the theorem, one should understand it just by the common sense, because we are dividing them, so they should be non-zero, norm X, right? Now you see, we got the left hand side, but right hand side is something different from what we want, right? And this is anyway something which is unknown to us, therefore we cannot consider this as an estimate. Somehow we have to get rid of it and bring something which is known quantity to us. Other than this, these two are known. Given the vector norm and the corresponding subordinate matrix norm, we can explicitly compute the norm of A inverse and norm of B minus B tilde. But this is something which is not known to us. Somehow we have to replace it by a known quantity. Let us see what to do for this. Yeah, for this, let us go back to our linear system AX equal to B and take the norm on both sides. That is, norm B is equal to norm AX, and again use our property of this subordinate norm. You can see that how crucially we are using this property. Once you use this property, we get this. Now you see, from this inequality, we can write norm X greater than or equal to, you bring norm A to the other side and make it in the denominator, right? So norm X is greater than or equal to norm B divided by norm A, right? from here, you can take this to the right hand side and this entire thing to the left hand side. That gives you 1 by norm x is less than or equal to norm A into norm B. Remember that we wanted the relative error in x tilde. Therefore, we wanted this quantity, right? And that is less than or equal to this quantity times 1 by norm x, right? Because we divided the left hand side by norm x, the right hand side should also be divided by norm x, right? So once you have this, now you see we have an estimate for norm x nicely here, and that you try to put here, and that gives you this is less than or equal to this entire thing, and this thing comes here. And how does it look? Well, that looks like this, right? Norm x minus x tilde divided by norm x is less than or equal to norm A is coming from here. Remember, we have norm x here and we have norm x here. And that we are now replacing by this. So norm A is sitting here. Norm A inverse is already there. And B minus B tilde is there. And divided by B is coming from here. So this is exactly what we want to prove in our theorem. So with this, we have proved our theorem. It's a very simple yet very powerful theorem. It says that if you commit an error in the right hand side, then the corresponding error in the solution, remember, we are not committing any error in the solution, okay? We are just taking AX equal to B. It's not approximately equal to. And similarly, AX tilde is exactly equal to B. It means X and X tilde are exact solutions of the systems, okay? With that in mind, you can see that the exact solutions of these systems and their relative error is estimated by this quantity, right? And what is the constant appearing on the right hand side? That is norm A into norm A inverse. This constant depends on A. Of course, it depends on the vector norm that you take, because you give me a vector norm, I will correspondingly find the subordinate matrix norm of the vector norm, put that together and get this inequality, right? That is how our theorem went. Remember, this matrix norm is the subordinate norm. Why? Because by using this property, therefore you cannot work with some matrix norm that you like and some other vector norm that you like. No. You have freedom to choose your vector norm. Once you choose your vector norm, the matrix norm should be the subordinate matrix norm of that vector. This you have to keep in mind. Whether you are doing some general problem or some particular problem where the vector norm is given, you have to remember this. From the examples point of view, if we are working with some specific vector norm, it will be one among the L1 norm, L2 norm, or L infinity norm. And we have explicitly stated the formulas for the corresponding subordinate matrix norm. So you have to remember them and correctly use them in your examples. So once you know what is the subordinate matrix norm that you are going to use, and if your matrix A is also given, you can explicitly find this constant. And once B and B tilde are given, then you can also find this. Therefore, this upper bound can be explicitly found even without knowing how the solution looks like. Okay, so from this expression, you can clearly see the importance of this constant. Okay, in fact, you can go back to the context of functions that we discussed in the previous chapter. There also we had this, right? F of x minus f of xa divided by f of x is actually f dash of xi will come from the mean value theorem, but that we will just replace by x, just an approximation. Therefore, it should be approximately equal to divided by f of x into x modulus times x minus xa by x, right? That is what we obtained in our initial calculations. And from there, we got the motivation to define this quantity as the condition number of the function. The same idea is also going through in this case, and we define the number norm A into norm A inverse as the condition number of the matrix A. Let A be an n cross n invertible matrix. Let a matrix norm be given that is subordinate to a vector norm. Generally, it should have been written in the reverse way. That is, given a vector norm, we should take the corresponding subordinate norm. Okay. Then the condition number of the matrix A is defined as this constant, and that is generally denoted by kappa of A. Well, if I give you an invertible matrix A and ask you to find the condition number of the matrix, you just cannot find it, but I have to also give you a vector norm. Okay, because the condition number is defined based on what vector norm I give you, and then you will go to get the corresponding subordinate matrix norm, or I may give you directly the subordinate matrix norm. Okay, so if I give you a norm, you first make sure that it is a subordinate matrix norm. Well, just the plain definition of condition number, you may not need it, but if you want to use this definition into any of your further analysis of linear systems, then you need this norm to be a subordinate norm. Otherwise, this will not go through, and so you really don't know why this is important if this inequality is not going through with that matrix norm. So always fix the subordinate norm and work with the condition number. That's always good. Well, from the estimate that we have established in the last theorem, we can see that if the condition number is small, then the relative error in the solution of the linear system is also small whenever the relative error in the right-hand side vector is small. On the other hand, if the condition number is large, then the relative error in the solution of the linear system could be very large, even though the relative error in the right-hand side vector is very small. Well, let us illustrate this interesting fact by an example. Consider the linear system with right-hand side vector as 0.7 and 1. And our linear system is therefore given by this, where your matrix A is given by 5, 7, 7, and 10, right? You can immediately see that the solution of this linear system is x is equal to 0, 0.1. Let us make a small error in the right-hand side vector B and call it as B tilde, which we took as 0.69 and 1.01. With this, the corresponding linear system is given by this. Note that the coefficient matrix is exactly the same. We have not committed any error in the coefficient matrix. Only on the right-hand side vector, we made a very small error. And that gave us the solution x tilde as minus 0.17, 0.22. Well, let us measure the relative error in x tilde when compared to x. And also we will see the relative error in B tilde when compared to B and see how they compare with each other. The relative error in the solution, remember, I am using L infinity vector. Whenever you talk about the relative error of the vectors, you have to first fix the norm that you are going to work with. In this particular example, I am going to fix my norm as L infinity. Remember, If I want to work with a physically realistic situation, I should have fixed Euclidean norm as my vector norm. But when we go to do the corresponding subordinate matrix norm, we need to do little more calculations with eigenvalues of A transpose A and all. So I don't want to do that. I want my life to be little simple. Therefore, I took L infinity vector norm because the corresponding subordinate norm is relatively easy to compute. That is why I took L infinity norm. Similarly, one can also take L1 norm, but I chose to take L infinity norm. And with respect to that norm, the relative error is given by 1.7. It means 170% error is committed in the solution. That's really huge. Let us see what is the relative error in the right-hand side vector. Of course, we have to use the same vector norm. Once you fix the vector norm, throughout the problem, you have to use only that norm. You cannot change step to step. You cannot change the vector norm. And that gives around 1% as the error. So you can see that you committed 1% error in the right-hand side vector, and that gave rise to 170% error in your solution vector. Recall, you have not made any further error in the solution. You got the exact solution of your system, but only thing is your right-hand side was not what you actually interested in. There was a slight 1% error in the right-hand side vector, and then you computed your solution of the system exactly, but still your solution has 170% error when compared to the solution that you intend to get. That is the relative error. Who is the culprit for this? Well, let us go back and see what is the condition number of the coefficient matrix A. Well, the condition number of the coefficient matrix is 289. Okay. So this seems to be pretty large. Why? Because you have got 170% error. Therefore, even 289 as the condition number seems to be very large. Remember how I got this number? I computed A infinity times A inverse infinite norm. And what is this infinite norm? You should go back to the corresponding theorem in the last lecture and see what is the corresponding subordinate matrix norm for the L infinity vector norm. You use that formula for A and A inverse and compute this number. That will give you 289. I leave it to you to check if you also get the same number. Well, this example confirms that even if you make a small error in your right-hand side vector and then go to compute your solution of the linear system with that right-hand side vector where you committed mistake, then your solution may have a huge error if your coefficient matrix has a big condition number. So whenever you are working with a coefficient matrix whose condition number is very big with respect to whatever subordinate norm that you fix, okay, that is not important because we are working with finite dimensional space. Therefore, if you use one of the three norms, the result will be the same for the other norms also because of the equivalence nature of the norms. Okay, numerically they may be different, but qualitatively their behavior will remain same. If you observe the behavior of that system with respect to one particular norm, the behavior will more or less the same in other norms also. Therefore, you don't need to worry about that. You fix any of the three norms that we have introduced, you find the condition number of the matrix A. If that is a large number, then you have to be very careful in working with that system because that system will be very sensitive to any error that you commit, not necessarily the right-hand side. Okay, any error that you commit, remember when you go to compute the solution on the computer, You will also make error during calculating the solution using any method that you use, even Gaussian elimination method with partial pivoting, you may be doing some small error there, right? So you have to be very careful. That is the overall moral of this story. A large condition number coefficient matrix is vulnerable to any small error in the computation. So with this, we will also define what is called ill condition and well condition. This is not something new to us. We already introduced these names with respect to function evaluation. Let us now extend our idea to matrices also. A matrix with a large condition number is said to be ill conditioned, whereas a matrix with a small condition number is said to be well conditioned. Again, small and big depends on how much you can tolerate the error in your problem and also how good your computer is. So we really cannot quantify how big or how small before deciding whether something is ill conditioned or well conditioned. It purely depends on your own situation. There is a very famous matrix called Hilbert matrix, which comes quite often in many practical applications. Even you don't want it, it just comes. Okay. The matrix is given like this. Hn is equal to 1, 1 by 2, 1 by 3, like that it goes on, 1 by n. Similarly, in the column also 1 by 2, 1 by 3, like that it goes till 1 by n. Now in the second row, you start with 1 by 2, therefore the next one will be 1 by 3, 1 by 4, and goes on till 1 by n plus 1. Like that it goes on. Since the last row starts with 1 by n, from there it goes as 1 by n plus 1, 1 by n plus 2, sorry, there is a mistake, and so on till 1 by 2n minus 1. This is called Hilbert matrix. As I told, in many applications, we come across Hilbert matrix as the coefficient matrix for our linear system. Let us try to see how big the condition number of this matrix is. Let us just take n is equal to 4, and you see the condition number of H4 is given by this number. I think I have taken the L infinity norm in computing this, and you can see that this 4 by 4 system with the coefficient matrix having condition number as 28,000. So how much it will be sensitive to any error that we commit in our calculations. So whenever you are dealing with such matrices, you have to be very careful in handling the other parameters, and also the computation that you do should be with very high precision. Otherwise, you may land up with a solution which may be several 100% relative error. The next interesting and important question is, what kind of matrices will be with large condition number? Well, it may be very difficult to categorize those matrices with large condition number. However, we can give some partial answer to this question. This is done in the form of a theorem. Consider an n cross n invertible matrix A. Then for any singular matrix B, which is n cross n, we can say that 1 by condition number of A is less than or equal to the relative error in B when compared to A. And of course, the matrix norm that is used here is a subordinate matrix norm with respect to some vector norm. It can be any subordinate norm. What we can understand from this inequality, let us try to see if your matrix A is very close to some singular matrix B, say, in the sense that the norm of A minus B is approximately equal to 0, then you can see that the right hand side is 0. And since the condition number is a positive number, you can see that this will be, of course, greater than or equal to 0, and hence 1 by kappa of A is very much close to 0. It means kappa of A is a very large number, almost infinity, right? So that is what we can infer from this inequality. It means if your matrix A is in some sense very close to a singular matrix, then surely the condition number of that matrix will be very large. Well, let us see how to prove this theorem. By definition, 1 by kappa of A, that is the condition number of A, is given by 1 by norm A into norm A inverse. You keep 1 by norm A as it is and apply the subordinate norm's definition to norm A inverse. That is maximum over all non-zero vectors X of norm A inverse X divided by norm X. This is the definition of subordinate matrix norm. Well, the definition is little different, but we can derive this result from the definition. We have seen it in the last class, so I'm just using that expression for subordinate matrix norm. Now, what I will do is I will remove this maximum, and thereby I will have less than or equal to 1 by norm A into 1 by A inverse of any vector Y, right? So what we got is this inequality for the condition number of the matrix A, which is satisfied by any vector Y. Now let us take a vector Z, which is defined by A inverse of Y. Then we can write the above inequality as 1 by condition number of A is less than or equal to 1 by norm A into, instead of Y, I'm just putting A times Z, and therefore I have norm AZ divided by norm Z. Since Y is arbitrary, even Z will be arbitrary. And in particular, you choose Z such that BZ is equal to 0. Remember, this inequality holds for any Z. In particular, for that Z for which BZ equal to 0 also, it will hold, right? So I will choose a non-zero vector Z such that BZ equal to 0. How is that possible? Well, B is singular matrix, therefore this is possible. Now, since BZ is 0, I can always write the numerator of the right-hand side of the above inequality like this. And now I can use our well-known result, norm AX is less than or equal to norm A into norm X, right? That I will be using here to get this step, and the denominator is kept as it is. So Z gets cancelled, and we have norm A minus B divided by norm A. And this is precisely what we want to show. So as I told you, if A is close to a singular matrix, then its condition number will be very large. That is what this inequality says. Let us illustrate this through an example. Consider the matrix B, which is equal to 1, 1, 1, 1, which is a singular matrix. You make a small perturbation of this singular matrix and consider another matrix A, which is 1, 1 plus epsilon, 1 minus epsilon, and 1 for any positive epsilon. However small it may be, you can see that A is an invertible matrix and its inverse is given by this. Let us use L infinity norm in our computation. Therefore, we know what is the corresponding subordinate norm that we have to use. When you use that subordinate norm, you can see that norm of A is equal to 2 plus epsilon, and similarly, norm of A inverse is equal to epsilon square into 2 plus epsilon. Therefore, the condition number of the matrix A is, by definition, norm A into norm A inverse. That gives us 2 plus epsilon by epsilon the whole square, which of course is greater than 4 divided by epsilon square. Now you can see that if you take epsilon tending to 0, you see that your matrix A is tending to B, right? And you take some very small epsilon, you will see that your condition number will be something greater than this number, where epsilon is very small. Therefore, this number is very large, and your condition number is bigger than that number. For instance, you take epsilon something less than 0.01, the condition number will be greater than 40,000. Now you can imagine that if we are working with such a coefficient matrix, it will be very much sensitive to any error that you commit in your calculation. So you have to be very careful with those matrices which are very close to some singular matrix. I hope from this example, you can intuitively understand what we mean by saying that a matrix is very close to a singular matrix. This is only one situation in which we come across a matrix which has big condition number.